The medieval history of calculus. The first form of modern-day calculus took place in the 11th century with Arab mathematician Alhazen finding the volume of the paraboloid. This shape, pictured right, is made by rotating the graph of a parabola around the z-plane. Alhazen used the dith method of calculating the volume, separating the radius of the ith disk to a minus a times I squared over n squared and thickness to b over n. Taking out all constants, we are left with the summation of a fourth degree polynomial, which Alhazen numerically proved equaled the equation below. As you can see, combining all terms, this equals the same result as via modern integration. This is considered by many to be the first instance of calculus in history, with Alhazen using integration techniques before rigorous integration had been invented.
So now we move on to Newton's contribution to calculus, in particular his method to determine tangents, as prior methods could not be applied to all curves. Newton developed this method around 1665 by analyzing known curves, then determined whether the method is general and applicable to all curves. He begins with a mechanical curve, where point xy has velocities q in the y-axis and p in the x. He allows an infinitely small amount of time to pass, so that the point moves to x plus o and y plus oq on p. As both points lie on the same curve, the new coordinates were substituted into the known equation. He then sets O to be 0, and the ratio of velocities, q on p, determines the direction of the tangent. Thanks to this method, the direction of tangents could be calculated for all curves.
Independent of Newton, another mathematician, Leibniz, began to develop methods of calculating the area under curves for use in his mechanical calculator. To do this, he needed a powerful and flexible notation. In 1673, it was common practice to view the area under curves as the sum of all vertical heights. This process can be represented today by using rectangle area approximations with a common width. If the width becomes infinitesimally small, then it was believed that the area under the curve was given by the sum of all heights. Leibniz originally represented the area under a curve by the notation omnia L. However, omnia was later changed with a long S script representing the sum of all. Additionally, at the time it was known that areas and tangents were related. Leibniz realized that the instantaneous tangent of a curve was given by the difference in height between two ordinates infinitesimally close together. Therefore, d was used to signify the transformation of calculating the tangent to a curve. By 1677, Leibniz finalized the power law rule of integration and differentiation. Furthermore, he had also formulated the product and quotient rules of differentiation.
Over the next 100 years, Leibniz and Newton's methods were clarified by mathematicians by replacing infinitesimals with limits. Applications of derivatives include optimization, which is used to find the best way to accomplish a task; related rate, which is the study of two variables that change with time. Newton's method finds an approximation for the x-intercept. Linear approximation finds a tangent to a curve, and the mean value theorem represents the relationship between two functions with the same derivative. Applications of integration include distance, velocity, and acceleration, where they can be derived from each other. Work is represented through changing distance or force over time in a summation. The center of mass can be found using concepts of torque, where the center of mass is the balance point.